Now let us continue finding Fourier transforms for other standard functions. Now we'll start with sampling function. Now, sampling function looks like this, right? Looks like this. So this is nothing but Fourier transform of a rectangular function. This is nothing but Fourier transform for a rectangular function, right? So for gate function, what do we know? Gate function is denoted by g tau of t, right? For a gate function, g tau of t or rectangle t by tau. You can denote it in either way. You can call it g tau of t. You can call it g tau of t, or you can call it rectangle t by tau, or you can also call it pi of t by tau. These are all the notations for gate function, right? For a gate function with amplitude a and a width of tau, the Fourier transform is given by a tau into sampling omega tau by 2. This is what we saw in the previous slide, right? See here, g tau of t has the Fourier transform a tau sampling omega tau by 2. Now we'll try and apply duality principle here, duality property. What does duality property say? If f of t has Fourier transform, f of omega, then capital F of t has Fourier transform 2 pi into small f of minus omega, right? Here small f of t is nothing but a into rectangle t by tau. Capital F of omega is a tau sampling omega tau by 2. Now in place of capital F of t, I am going to write in place of capital F of t. I know capital F of omega. Now in place of omega, I am just going to substitute t. So a tau sampling t tau by 2, right? A tau sampling of t tau by 2 has the Fourier transform 2 pi into what is small f of t? It has the amplitude a and it is a rectangular function, right? Amplitude a and a rectangular function. I'll call it g of width tau and a function of t. So in place of t, what I'm going to have? I'm going to have minus omega, right? In place of t, I'm going to have minus omega. The same thing, instead of g tau of minus omega, I'm writing rectangle of minus omega by tau. Okay. So this is by applying duality property. This we have got by applying duality property. Now, what is my aim? I have to find the Fourier transform for sampling function, sampling of t. So let us continue further. Now, I will make a as 1. I'll assume a is equals to 1. So what will happen? Tau sampling t tau by 2 as the Fourier transform, 2 pi into rectangle of minus omega by tau. This 2 pi I will get to the other side. It is tau by 2 pi on the left hand side, right? Then, since rectangular function is an even function, right? Rectangular function is always a even function, right? So instead of minus omega, I can have omega, right? Instead of minus omega, I can have simple omega. Then if with tau, instead of tau, if I put it as 2w, if I substitute tau is equal to 2w, right? In place of tau, I have substituted 2w. Now I'll simplify this further. This here, what happens? 2 and 2 gets cancelled. Here 2 and 2 gets cancelled, right? So what am I left with here? I have omega by pi sampling of t, sorry, w by pi sampling of t w. It has the Fourier transform, rectangular function of omega with width 2w. Now sampling of wt, right? Sampling of wt, that is nothing but sine wt by wt, right? When is this 0? When is this 0? When wt is equals to plus or minus n pi. When wt is equal to plus or minus n pi. That means when t is equals to plus or minus n pi by w. So let me draw my sampling function here. Let me draw my sampling function here. My sampling function. So this has to be a decreasing sinusoidal kind of thing, and on the same thing on the negative side. Okay. So at t is equals to plus or minus n pi by w, my sampling function crosses the x-axis. So at 0, when n is equal to 1, it is pi by w. Then at 2 pi by w, same thing here, negative pi by w, and so on, right? This is my function. So, and my amplitude of the sampling function is w by pi. Amplitude of the sampling function is w by pi. If this is my sampling function, what will be my Fourier transform? What will be my Fourier transform? Fourier transform is nothing but a gate function. It's nothing but a simple gate function or a rectangular function. Now what are the parameters of this gate function? The width is 2w, so it extends from minus w to plus w, right? It is a function of omega, and the amplitude is 1. Amplitude is 1, right? Amplitude is 1. So this is how I can find the Fourier transform for a sampling function using duality property, right? So this is how duality property is applied to find the Fourier transform. We'll move on to the next signal, that is a constant function. We have to find the Fourier transform of a constant function. So now there are many ways to find Fourier transform of a constant function. So first of all, if you integrate a constant function minus infinite to infinite, if you integrate some constant function f of t is k, right? This is minus infinite to infinite dt. What will happen? K into integration of dt is t from minus infinite to infinite. It becomes infinite. So using the formula of Fourier transform, that is minus infinite to infinite f of t e power minus j omega t dt, we cannot find the Fourier transform of constant function. So how will we find the Fourier transform of the constant function here? We will use some properties. Using some properties, we'll try to find the constant function Fourier transform. We are doing this because it is one of the standard functions. Okay, otherwise we will not be doing this. So we already know delta of t, right? Delta of t, that is my impulse function. It has a Fourier transform of 1, right? Now, using duality property, what does duality property state? According to duality property, capital F of t has the Fourier transform 2 pi f of minus omega, right? 2 pi f of minus omega. So what is capital F of t? My capital F of t is 1. So it has a Fourier transform. 2 pi del of minus omega, right? This is according to duality property. Now let me multiply. Okay, before multiplying, this del of minus omega here, if I can draw the del of minus omega, this is my omega axis. Del of minus omega is right here when omega equals to 0, right? This is where my del of minus omega is located at omega equals to 0. So if you look at this graph, we can conclude that this is a even function of omega, right? In place of omega, if I put minus omega also, it's the same thing. So I can replace minus omega with omega. So I can write 1 has the Fourier transform 2 pi del of omega. Now I can multiply it with a constant on both sides. If I multiply this with k, I can multiply this with k. It's just a multiplicative constant. So k has a Fourier transform 2 pi k into del of omega, right? K has a Fourier transform 2 pi k into del of omega. That is my Fourier transform of a constant function, right? Fourier transform of a constant function. For a constant k, the Fourier transform is 2 pi k into del of omega. This is a simple method of finding. Here we are showing you a different method of calculating the Fourier transform for a constant function. Now I have considered a gate function shown in this figure here. Gate function is extending from minus tau by 2 to plus tau by 2, right? Minus tau by 2 to plus tau by 2. It has an amplitude of k. So what is my Fourier transform for gate function? The amplitude into the width of the function, that is k into tau, sampling of omega tau by 2, right? This is the Fourier transform for my gate function. Now when I make tau infinity, when tau tends to infinity here, when tau tends to infinity, minus tau by 2 and plus tau by 2 also tend to infinity, right? In place of tau, if I put infinity, this goes to minus infinity and this goes to minus infinity. So what happens to f of t? F of t can be approximated to this function here, right? Approximated to this function with amplitude k, right? F of t can be approximated into this function at the bottom of the screen. So f of t becomes a constant function. So f of omega is nothing but Fourier transform of the constant function k. That is nothing but I am taking this in the limit tau tends to infinity k tau sampling omega tau by 2. Now that is equal to I am multiplying and dividing by 2 pi. So 2 pi k limit tau tends to infinity tau by 2 pi sampling omega tau by 2. Right? Now when tau goes to infinity, right? When tau goes to infinity, this or let me say when k goes to infinity, k by pi sampling of kt is nothing but a simple impulse function. This is a simple impulse function, right? So this is what we saw, right? Sampling function. It was like this in the previous slide. It was something like this, and the amplitude was k by pi. Amplitude is k by pi. When k goes to infinity, right? Now when k goes to infinity by pi. At this point, my amplitude is infinity, and at all other points, it becomes 0, right? Because what is the zero crossing here? Zero crossing is t is equals to plus or minus n pi by k. When k goes to infinity, if I substitute infinity in place of k, t is equal to plus or minus n pi by infinity, which is equals to 0. So everything else here vanishes. All the signal here vanishes. We will only be left with one impulse at t is equals to 0. That is nothing but delta of t, right? So in place of this entire thing, I can just substitute delta of, here t is equals to omega, so delta of omega. That is how I can arrive at this Fourier transform, considering our constant function as a limiting case of rectangular function, right? This is slightly complicated. This is the simpler method of finding impulse Fourier transform of a constant function. Then Signum function, right? Signum function. Signum function is defined as -1 at t less than 0, plus 1 at t greater than 0, 0 at t equals to 0. It looks something like this. Again, Signum function also, if you actually take the integration, it is not absolutely integrable. So we'll try and express this as a limiting function. So I will consider an exponential signal here and another exponential signal here, right? These two are my exponential signals. This is one exponential signal and this is another exponential signal. So what I can write here, what is this signal given by? This is a decaying exponential. Decaying exponential is given by e power minus at, right? E power minus at, and it is only present for the positive side of x-axis or time axis. So it is just nothing but multiplied with u of t. And here, if you look at this, this is a rising exponential, right? From smaller values, it is going bigger, right? This is negative value and it is increasing. So how can I write this function? It is nothing but e power at, e power at, only for the negative axis of t. So u of minus t, u of minus t, right? Now, if I take the limiting case, if I make a 0, right? If I make a 0, what will happen here? If I make a 0, if I consider limit a tends to 0, e power 0, this becomes 1, and u of t. So on the right hand side, I have u of t, that is 1, right? And here, if I make a 0, I have u of minus t. So that will be something like this, u of minus t. This is my signal here, and this one is shown here. Now if I subtract these two signals, the first signal minus the second signal, what will I get? The first signal minus second signal. I'll draw it in a different color here. First signal minus second signal. So on the positive hand side, or on the positive time axis, what do we have? The first signal, it is 1. In the second signal, on the positive side, it is 0. So 1 minus 0 is 1, right? On the negative side, in the first signal, it is 0. And in the second signal, it is 1. So 0 minus 1 is minus 1. And at origin, we have 0. At origin, we have 0. So this is nothing but a signum function. So how can we express our signum function as a limiting case? Limit a tends to 0. This is the first signal, e power minus at u of t, minus the second signal, e power at u of minus t. So this is what I am considering as my signum function. Okay, this is how I will consider the signum function. So to find the Fourier transform of signum function, I am going to find the Fourier transform of this equation here, the limiting case. So let's take that equation and find the Fourier transform. So limit a tends to 0, I have taken outside, and I have integral minus infinite to infinite. So what I am doing here, I am separating this integral into two integrals, 0 to infinity and minus infinity to 0, right? Minus infinity to 0 and 0 to infinity. Then in the range of 0 to infinity, how does my signum function look like? 0 to infinity, it is nothing but 1, right? E power minus at u of t. What was my signum function defined as? In 0 to infinity, 0 to infinity, t greater than 0, it is e power minus at, and minus infinity to 0, it is e power at, right? The same thing. 0 to infinity, it is e power minus at into e power minus j omega t dt, and minus infinity to 0, it is e power at and into e power minus j omega t into dt. Now I will integrate and find the Fourier transform. Integration is similar to what we have done so far. We have done so many integrations based on this, right? E power minus a plus j omega t dt. So we'll just integrate, and these are my limits. Now let me substitute my limits, integration limits. In place of t, if I put infinity, e power minus infinity becomes 0 minus, if I put 0, e power minus 0 is 1, and I have a negative sign here, so this becomes plus a plus j omega, and then minus, if I put 0, e power 0 is 1 by a minus j omega, minus, if I put negative infinity, e power minus infinity is 0, right? So what do we have here? We have 1 by a plus j omega minus 1 by a minus j omega, right? We have 1 by a plus j omega minus 1 by a minus j omega. Now let me substitute my limit a tends to 0 here. So in place of a, I am just going to put 0. So a goes away. So I have 1 by j omega plus 1 by j omega, that is 2 by j omega. 2 by j omega, right? So my Signum function Fourier transform is 2 by j omega. The Fourier transform of Signum function is 2 by j omega. So how do I represent this in graphical form? So 2 by j omega. So now I have to find the amplitude and phase. So let me separate the real and imaginary parts. So let me just multiply it with minus j omega divided by minus j omega. What will I get? Minus 2 j omega divided by negative omega square and j square. J square is negative, so minus. So plus. So what am I left with? I have minus 2j by omega. Minus 2j by omega. This is the imaginary part, right? J, that is minus j 2 by omega. So my amplitude spectrum is going to be square root of real part square plus imaginary part square. My real part is 0. So the square root of imaginary part is imaginary part. So my amplitude spectrum mod f of omega is equals to my imaginary part 2 by omega, right? So what happens when omega is 0? When omega is equal to 0, my amplitude goes to infinity, right? It's going to infinity. That is why I'm representing this. So it goes to infinity. So this is how I will draw. As omega increases, my amplitude decreases, right? As omega moves away from the origin, my amplitude decreases. At origin, it goes to infinity. So it goes something like this. It keeps on going higher and higher, right? That is how I will draw my amplitude spectrum. So this is my omega, and this is my, in this direction I have f of omega, magnitude f of omega. Now similarly I'll look at phase spectrum. Theta of omega is nothing but tan inverse of imaginary part by real part. The imaginary part is minus 2 by omega by real part 0, right? So minus, I'll take it outside, that is nothing but minus tan inverse of two by 0, whatever it is, this whole thing reduces to infinity, right? Minus tan of infinity, right? It is undefined, right? It is infinity. Minus tan of infinity. Tan of infinity, when omega is positive, what happens? Here it is. Let me just rewrite this thing. When omega is positive, this is positive and this is negative. So I have minus tan inverse of infinity for omega greater than 0. And for omega less than 0, what happens? Omega is also negative and there is a negative sign. Both of them get cancelled. It is tan inverse of infinity. Tan inverse of infinity. Now tan inverse of infinity is pi by 2. So for values less than 0, it is pi by 2. And for values greater than 0, it is negative pi by 2. So that is how we will calculate the amplitude spectrum and phase spectrum for Signum function. Okay. Now let's move on to the next slide. Now we will see the Fourier transform for sine and cos. Cos omega naught t is my signal. So that in terms of exponential, complex exponentials, I can write as e power j omega naught t plus e power minus j omega naught t by 2. Now I'll find the Fourier transform of cos. Fourier transform of half of e power j omega naught t plus half of e power minus j omega naught t. This is by linearity property. Now I know what is the Fourier transform for 1, right? For 1, what is the Fourier transform? We have done this in the constant Fourier transform. Fourier transform for constant. For 1, the Fourier transform is 2 pi into del of omega, right? Del of omega. Now, if I have a phase shift on the time domain side, there will be a corresponding frequency shift in the Fourier domain. So if I multiply this with e power j omega naught t, then my Fourier transform will be 2 pi del of omega minus omega naught, right? This is by frequency shifting theorem. This is the frequency shifting theorem. Now I will divide by 2 on the left hand side as well as the right hand side. I can do that. Now what will happen? This is my time domain signal here, right? 1 by 2 e power j omega naught t. Its corresponding Fourier transform is pi into del of omega minus omega naught. Pi into del of omega minus omega naught. Suppose I have a negative sign here. This will introduce a positive sign here. So if I substitute these things in the equation, this is what I will get. My final Fourier transform. Pi into delta of omega minus omega naught for the first term and pi into delta of omega plus omega naught for the second term. So for cos omega naught t, the Fourier transform is pi into delta of omega minus omega naught plus plus pi into delta of omega plus omega naught. This is how the Fourier transform looks like. There is no phase term here. Okay, we'll just look at the amplitude spectrum. So this is the first term here is a impulse with strength pi, and it is located at omega equals to omega naught, right? Omega equals to omega naught. And the second term is the same impulse with strength pi and located at omega equals to negative omega naught. So this is for cos omega naught t. Now the same thing I can do for sine also. For sine, I will have e power j omega naught t minus e power j omega naught t. Let me just erase everything. I'll erase a few things here, and I will write for sine. Right? Let me take a different color here. So in place of cos, if I have sine, how will my equations change? So here, instead of a plus sign, I will have a negative sign divided by 2j. Right? Here I'll have 2j, here I'll have 2j, and instead of a plus sign, I'll have a negative sign. Right? So in this Fourier equations here, I have a 2j term here. I'll introduce a 2j term here. So what will happen? This is what it will look like. Sine omega naught t as the Fourier transform. For the first signal, I'll have pi by, sorry, no 2 there. What do I have? They're shown on the yellow color. In the yellow color, I have pi by j del of omega minus omega naught plus I'll have del of omega plus omega naught, right? Oh, instead of plus, sorry, here it's not a plus. It is not a plus here. I have a negative sign here. So this is also a negative sign. So how does my amplitude spectrum look like? Amplitude spectrum looks like this. At omega equals to omega naught, I have an impulse with strength phi, right? And at omega equals to negative omega naught, I have an impulse with strength minus pi. This is my f of omega versus omega, right? So this is for sinusoids. This is what we have seen now, right? There we had pi by j. Del of omega minus omega naught minus del of omega plus omega naught. Now what I'm doing, I took this to the numerator, so it becomes minus j, and I'm multiplying the negative sign inside. So this is what I will arrive at, right? This is for sine omega naught t. And then we'll look at unit step function. Unit step function, if you again look at it, unit step function, it is not absolutely integrable. If you integrate it over the limits of minus infinite to infinite, it becomes infinite. Again, because it is one of the basic functions, we'll try and find out the Fourier transform of unit step function based on some properties. So unit step function, I can write it as like this. This is my signum function, right? 1 and minus 1. This is my signum function. So let me just multiply it with half. So it becomes 1 by 2, and this becomes minus 1 by 2, right? This is 1 by 2 and this is minus 1 by 2. Now if I add a signal, a constant signal to it, let me say half, the amplitude half. Now what will I get? For the positive side, The first signal is 1 by 2 and the second signal is also 1 by 2, right? So it is 1. For the negative side, it is minus 1 by 2 plus 1 by 2. So it becomes 0, right? So it is nothing but a unit step signal. This is my unit step signal, and this is my half signum function, signum of t, and this is a constant function half. So unit step function u of t is nothing but half into signum function of t plus 1 by 2. Now let me take Fourier transform on both sides, and by linearity property, what can I do? I can separate these two functions. So it is nothing but Fourier transform of or 1 by 2 is a constant, so I can get it outside. Fourier transform of signum function of t plus 1 by 2 Fourier transform of 1, right? Fourier transform of 1. For signum of t, the Fourier transform is 2 by j omega. For 1, the Fourier transform is 2 by del of omega. So I'll just substitute those here. So I'll get 1 by 2 into 2 pi del of omega plus 1 by 2 into 2 by j omega. 2 gets cancelled. Here 2 gets cancelled. So I'm left with pi del of omega plus 1 by j omega. Right? Now let me draw the amplitude spectrum here. Let me draw the amplitude spectrum. How does it look like? There is an impulse at omega equals to 0 and strength pi, right? So this is that impulse at omega equals to 0. This is my impulse at omega equals to 0 and 1 by j omega, right? As omega increases, the Fourier transform amplitude decreases since omega is in the denominator. So that is how the amplitude characteristics for unit step function is drawn. Now next one is Gaussian pulse. You can try this as practice using the let me say the analysis equation. We will do one, the other one you can try and practice. So let me just try the first equation, Fourier transform pair. So e power minus pi t square. For that we have to find the Fourier transform. So f of omega, let me take a different color. F of omega equals to minus infinite to infinite, f of t into e power minus j omega t dt. So instead of f of t, I'll write my Gaussian function, e power minus pi t square into e power minus j omega t dt. Now this one can be further written as minus infinite to infinite e power minus pi t square plus j omega t dt, pi t square j omega t dt. Now I'll take this expression here. I'll take this part here and I'll try to represent it in some different form. Pi t square plus j omega t. I can write pi t square as root pi whole square, right? Root pi t whole square. So I can, this is nothing but in the form of a square, right? Now plus I'll write as 2ab form. So 2 into what is my A? A is root pi t, and B, I have to find out B such that my 2AB term is equal to j omega t. So my B will be, in order to get j omega t, what should I multiply it with? I should multiply it with j omega by 2 root pi. So this is my B term. This is my B term, right? Now I have got a square, and this is my 2ab. So I will look for my b square, right? B square plus b square minus b square, right? So this is what is my final expression here, right? Pi t square plus these two gets cancelled, it is j omega t. I got my expression. Now I'll try to add b square and subtract b square. So what is b square? B square is nothing but j omega by 2 root pi whole square. So that is nothing but omega square by 4 pi. J square is minus 1. So b square is equal to minus omega square by 4 pi, and minus b square will be plus omega square by 4 pi. So this whole thing can be written as a square plus 2ab plus b square, right? A square plus 2ab plus b square. That is nothing but a plus b whole square. So what is my a? A is root pi t plus b is nothing but j omega by 2 root pi whole square, and I have plus omega square by 4 pi, omega square by 4 pi. So my f of omega can be written as minus infinite to infinite e power minus, this whole thing can be written as pi t square plus j omega t can be written as this expression, right? Root of pi t plus j omega by 2 root pi whole square, and I'll put a bigger bracket here, plus omega square by 4 pi, omega square by 4 pi into dt, right? Now let me simplify this further. So e power minus a plus b, so it is nothing but e power minus a into e power minus b, right? So e power minus a into e power minus b. So minus infinite to infinite e power minus root pi t plus j omega by 2 root pi whole square into, I have e power minus omega square by 4 pi. Now e power minus omega square by 4 pi is independent of t, so I can write it outside. E power minus omega square by 4 pi, right? I can write it outside, and I have dt. Now I'll make a substitution here. In place of this, I'll write u. I'll take u in place of my root pi t plus j omega by 2 root pi. So how will that change now? It is equal to e power minus omega square by 4 pi, omega square by 4 pi, integral minus infinite to plus infinite, e power minus u square, u square. So this is my u, right? What is dt if I in let me write it here. U is equals to root of pi t plus j omega by 2 root pi. Now if I differentiate du, here I will get root pi into dt, and this is a constant, so it will go to 0. So instead of dt, what can I write? Du divided by root pi, du divided by root pi, right? I'll erase this part here. Now this function here inside the integral, this function here is a even function of u, right? In place of u, if you put minus u also, it is the same thing, right? E power minus, instead of u, if you put minus u, you will get the same function, right? E power minus of minus u square is nothing but u square, so e power minus u square is the same thing. So it is an even function. So when it's an even function and has the limits minus infinite to plus infinite, how can I write it? I can change it to so this is my coefficient, divided by root pi. I can change it to integral 0 to infinity and multiplied by 2 e power minus u square du, e power minus u square du. And this is a common integral. This 0 to infinity is a 0 to infinity e power minus u square du is a common integral. Its value is root pi by 2. The value of this integral is going to be root pi by 2. So I'll substitute that value here. So I have e power minus omega square by 4 pi into 2 by root pi into, in place of this integral, I can write as root pi by 2. So all of this gets cancelled and I am left with e power minus omega square by 4 pi. That is what is given here, right? In place of omega, if I substitute 2 pi f, right? Omega is nothing but 2 pi f. So in place of omega, if I substitute 2 pi f, I'll get e power minus, sorry, in place of omega, I should substitute 2 pi f. So e power 2 pi f whole square, right? 2 pi f whole square is 4 pi square f square divided by 4 pi. 4 pi and this gets cancelled. So I have my final equation as e power minus pi f square, e power minus pi f square. E power minus pi f square. So if you look at this Fourier transform, right, e power minus pi f square, it is similar to my original time function e power minus pi t square. So if this is a Gaussian function, then a Fourier transform is also a Gaussian function. So that is what we will conclude. The Fourier transform of a Gaussian pulse is also a Gaussian pulse, right? In the similar way, we can also prove the second Fourier transform here. Similar way. That is left as practice. So Fourier transform of a Gaussian pulse is also a Gaussian pulse. So in the next video, we will continue some problems on Fourier transform.